Hello, class, and welcome to this pre-recorded CS 202 session. This is supposed to replace class at the time of this recording, which is tomorrow. But as you are watching this, it's probably June 15th. Today, I'm going to cover a few things. For one, I'm going to cover a little bit from the inheritance example that we talked about today. I said I would tell you why the code ran the way that it did, and that we were not seeing the special ability coming from the ranger. So I just kind of want to clear that up. After that, I will briefly introduce the assignment, the new assignment. And then after that, we're going to get started with pointers. The pointers part of this pre-recorded session will be pretty light. So hopefully you'll be able to follow along pretty well. So to begin, if you recall from class today, I had some code here. And we had made 3 classes, player classes, as if we were making a video game that was kind of Lord of the Ringsy, I guess, where the 3 classes, warrior, ranger, and mage, were inheriting from this player class that we made. And so warriors, magers, and rangers all have the same member variables up here, such as a weapon, some health, an ID, and then a damage variable. But then as we split out and we inherit from this class, each class that's inheriting from this, we'll call it a super class or a base class, will have some different abilities. So in the case of the warrior, they're just a little beefier, so they're going to have some more health. The ranger has the special ability to be able to dodge, and the mage has the special ability to be able to deal a critical strike. Now, when I ran this code, you should recall that we saw special abilities coming from the mage, but we did not see any special abilities coming from the ranger. So I am going to open up MOBA right now. I was looking at your assignments just now, so you should see a very familiar program on the screen in just a moment. Alright, so I already have this code loaded up, so I'm going to go ahead and compile that. And when we run it, you will see that this mage here happens to use a critical strike a few times. But this P0 character, which I guess happens to be the ranger, let's go take a look. Yep, that is P0. None of the special attacks are invoking. And the reason for this is because let's follow the calling path. So you'll see that mage M calls deal damage. And so if we go up to the mage M, you'll see that first we calculate whether or not a critical strike was dealt. And then if after that, we call receive damage on P2. Now, P2 happens to be the ranger in this case, but there's a crucial thing that we're missing here. And it's that the parameter here is actually of a player type. And so kind of what happens here is the ranger, as it's passed into this deal damage function, it is upcasted. It is casted to a player, and then we call receive damage from what? Not the ranger class, but the player class. And so this receive damage function never gets called, and we will address that later on in the semester. So for those of you who broke your heart, with this gaming code that didn't work, now we know that because Ranger was casted to a player, the received damage was called from the player class and not the Ranger class. So given that, this is some very similar code to what you're going to be doing in the assignment. So let me go ahead and pull that up for you real quick. This assignment is going to be hopefully the easiest one you've done so far. It should be just a light little assignment. Hopefully just to get your feet wet with a few things. So let me go ahead and grab the PDF here, which once again happens to be a few pages, but guess what? I'm just a very descriptive person. So I would recommend that you read it, but shouldn't take you too long at all. So we're playing with dice. This is assignment 3. And so I'll kind of start out with this. You are going to be working for a game development company, and you have been assigned to develop the 3-player classes, similar to what we did today, for a riveting game called Roll and Win. This game is very simple, and likely no one's going to play it, but you decide not to voice your opinion because you don't want to make the game designer feel bad. I'm the game designer, so of course you don't want to make me feel bad. So how's this game work? Well, 3 players will connect to the online game, and then each player is assigned one of the 3-player classes below. There will always be one of each class in the game. So the first class is the thick skin class, meaning that they're kind of tanky. You know, thick skin usually means that things don't bother you, but in the case of this assignment, it means that you can lose a lot and you won't get ejected from the game. There's also the Survivor class and the Genius class. So each player, the thick skin player, the Survivor player, and the Genius player will all roll their dice at the same time. Their die at the same time. The player with the highest number wins the round. And so the game will continue for multiple rounds until one player is left. Each player can only lose so many times before they are ejected from the game. So as I said, the thick skin player is going to be able to lose more times, not really let it get to them, than say the Survivor and the Genius class. So that's it really. But you may ask, why are there multiple classes? Well, to spice up the game, each class has its own special ability, just like we practiced today in class. So I already described this one, right? The thick skin class is granted 1 extra loss before ejection. So this means they can lose 4 times, and the other classes are only going to be granted 3 losses. Now, the Survivor class has a 5% chance to not count a lost turn towards their loss count. So a Survivor class could potentially lose infinitely, but never get ejected because they keep using their special ability. So in a way, the Survivor could survive more rounds than a thick skin class, but the Survivor only has 3 to start. So these 2 classes are similar, but they're different. And finally, the Genius class has a 5% chance to add 2 to whatever their dice roll was. If a Genius rolls a 4 or greater while invoking their special ability, they are guaranteed to win that round, because 4 plus 2 is 6, and the other 2 classes cannot roll higher than a 6. They could roll a 6 in which they'd all tie, but hopefully you understand that. As I said earlier, this code is perfect for inheritance. All players roughly have the exact same design aside from their special powers. So your job is to code up the 3 derived classes and change some code. Everything else is provided for you. So we're going to introduce this thing today about multiple files. You haven't used this before, I'm pretty sure, but we're going to actually use 3 files to create one program. So the 3 files that there are the player.h, that's the player.h file. Now this only includes the prototypes for the classes and a prototype for a global function. And then we have the player.cpp file. Now this is referred to as the implementation file, and we'll include this in the notes after I'm done talking about this assignment. The implementation file includes the definitions for the class functions and the global function. So pretend, let me show you the previous example that we had the other day, probably when we were talking about classes. You should be able to recognize that code, hopefully. I'm just going to kind of give you the idea of what these two files would look like. So if I open up classes 2, you'll notice that I have the point2d class here. And notice that most, not all, but most of the function definitions are actually outside of the class, aside from a few where I was just making a point, right? So pretend that this bit is stored in player.h, and then all of these are stored in player.cpp. So one file, the header file, is a very clean, nice looking file. You can just go in there and look at how things are designed. The implementation file is the CPP file that includes all the definitions for everything that's in that header file. You'll get plenty of examples of that. I'll even show you how to run this code. It's also included in the PDF. And then finally, there's main.cpp. Main.cpp is always required because of int main. And it's required to run our code. So I'll show you all three of these files. Just a moment. Here I include the entire definition for the player class. Guess what? This class is 100% coded for you already. So if you're just looking for an understanding of how this class works, go ahead and read this. I kind of provide some things. Likely you're going to want to read about this thing here, the player int. You're probably going to want to read about the roll dice function. You're going to want to read about the record loss function. You're going to want to read about the chance for special power. You're going to want to read about the get PID. But pretty much every other one you could skip over if you really wanted to. And you're going to want to read about this one too. The number of turns each player has before they are ejected. So that's just provided for you. So let's go look at it in our code. This is player.h. This is where we start. I will also talk a little bit about these, so don't get spooked. They're really nothing too scary. So notice here, here's the player class, and look at how pretty it is. Just sitting there all nice. We can see exactly what's in there. And then down here is where your code goes. So I haven't uploaded this yet, but I will do something like this, where I say, hey, your code goes here, as always. So in this file, you're just going to include the prototypes for these classes. So pretty much the class definition for the thick skin, the survivor, and the genius class. In addition to this, there's a prototype for the play game function, and that's included in this header file as well. So that's player.h. And before we get into the derived classes, I'll also show you player.cpp. Notice here that we are including this header file, player.h. And in here, I just have all of the definitions for every constructor, destructor, and function that belongs to the player class. So in here, you'll add your code for your either constructor and or function definitions here. And then you can see that the global function definition for this is the play game function. I should have changed that, is sitting here. And so you can look at that if you want, but this will just have all of the players roll their dice. I did that part for you. So that's pretty much it. In main, you'll see that we include that player.h file here. And you can see that this game is just run from main in a little while loop down here. And it's going to play the game multiple times until one person wins. So these are your 3 UMLs. Look at how tiny they are. They're so small. For the thick skin class, all you have to do is the constructor. That's it. It's only going to be the constructor. Now for the survivor class, you're going to want to include the constructor and this function record loss. because recall that survivor class may not count a loss towards their total number of losses. So in that record loss function that you're going to override, you're going to want to potentially not subtract 1 from their num turns. In the genius class, notice that they're overriding the roll dice function because a genius has a chance to add an extra 2 to whatever their dice roll is. You're going to be overloading this function as well. Overriding, excuse me. Not overloading, but overriding. You're also going to want to include that constructor. So all 3 of them have constructors, and only 2 of them have function overrides. So notice here I say you have to code 100% of the derived classes. This includes adding the class prototypes in the player.h file, as well as the class function definitions to the player.cpp file. I tell you exactly how this works, so please just read this. It's pretty light. It's pretty light reading. Of course, I'm a little bit descriptive here, so maybe we can talk about them. Just specifically these ones. So in the record loss function, the first thing you should check for to see is if that player invoked their special power. So I talked about this a little bit in class today, but if you look here in player.cpp, you'll see that there's a function called chance for special power. Now this should be 5, not 10. And you'll see that this roughly has a 5% chance to return true. So whenever you call this, it returns either true or false. And so when you call that, if it happens to be true, then they've invoked their special power. And in this case, you can print a little message that says special invoked. And player ID, you're going to replace this P dash pound sign or hashtag with the actual player ID, and it's going to say survived for 1 more round. But if that function returns false, once again, if that chance for special power returns false, just record a normal loss, right? Just subtract 1 from the num turns. And perhaps you're going to be doing that by calling the exact same function from the base class. In the genius class, pretty much the exact same thing happens. You call this function, chance for special power. If it happens, go ahead and print a special message. And if it did happen, you're going to want to add 2 to the original dice roll, or you're going to add 0 to the original dice roll. You are going to have to call that function, the base class roll dice function, to get the actual value of whatever their die was, but then you're going to add either 2 or 0 to it. So once you do that, you're pretty much done. You just have to alter some code. Now this is the easiest thing of this whole assignment, I swear. So this code is already designed to compile. So this code will compile and run. I'll show it to you. And the only reason it does that is notice that the play game function here takes a player, and a player. And if you look in main, you'll see that it takes a player, and a player. So pretty much you just have to replace these 3 players with the derived classes, probably Thickskin there, Genius, and Survivor, something like that. As well as in here, you're going to have to replace them here, the same type order. And then in here, you're going to have to replace them as well. And once you do that, if your code works, you're going to start seeing some special powers be invoked. So let's run some test runs. This is how you compile your code. I need to fix this. I will fix this before I upload this. I was using the last assignment as a template. So you will see a better version of this PDF on Web Campus. And I will come up with some comprehension questions as well. So just ignore that part. I did not get very much sleep last night, so obviously I'm going to forget some things every now and then. So we're going to pull up Bobby here. And we're going to load up first the code that you are provided, the student's code. So that's the code that I just showed you, and it will compile and run as is. Now the way that this compiles is very simple. For every CPP file, you have to include it in the compile statement. So there's actually 2 CPP files, right? Let's go take a look. There's 2 of them. Here they are, player.cpp and main.cpp. So for every CPP file there is, you have to include it in the compile statement. First we'll start with main, and then we'll start with player. Now we're off to the races. It has compiled, so we can just /a.out, and we're going to run the code here. So round 1, notice they all roll a die, and someone wins. It looks like the player 0 here wins, and P1 and P2 lost that round. And the game just continues until someone lost, and it looks like P0 kind of had an amazing game. So if we run the code again, we'll actually get different results. I've designed it that way, hopefully. Yep. And so now we're going to run my solution. With any luck, we should start seeing some special powers. Run the same compile statement. And it looks like I have messed up one little bit here, so just give me a second. Of course, I was changing the name of something last minute, and I got caught up doing something I shouldn't have been doing. So let me just take a quick look here, see what I did. That looks fine. And this, oh, I see what I did. All right, so we're going to give this one more shot. Sorry about that, folks. And thank you for bearing with me. So now I'm going to go ahead and just load that same code. This time it will compile. And then we're going to run it a few times. So let's see if we got any special invocations. Yes, we did. So notice at the start here, we just kind of had a regular roll. And then it looks like P1 lost that round. So P0 rolled a 5 and P2 rolled a 5, but P1 rolled a 4. And so P1 lost, but P1 happens to be the survivor. So you'll see that P1 lost that round, but then it's going to say, hey, special power invoked. P1 survived for one more round. And so then the game will continue. So if we happen to run this again, maybe we can see some special powers somewhere. Of course, it's only a 5% chance. So it's pretty unlikely that we see a special power invoked. Though, if you run it enough times, you will eventually see that P2 will, this is the Genius class, right? You'll see that they have invoked their special power. So I'll be uploading an updated PDF, and I will be uploading the sample outputs and the skeleton code. Let me know if you have any questions. Have a good time with it. It only should take you a very small amount of time, assuming that you followed the inheritance nodes pretty well. All right, so I'm going to open up a notepad here, and there's just a few things that we need to discuss before we really get into our pointers here. Okay, we're doing pretty good here on time. So I'm going to bring this up to be very large. And so the very first thing I talked about today was the implementation files. Okay, so all I'm going to do is just kind of tell you a little bit, or at least include the words that I said in the notepad. So as I said, the class, like the blueprint, is included in the H file. So someone can specify the general shape of a class without actually coding the definitions. That's kind of the purpose of the H file. In this way, we can compile different implementations of the class functions each time we run the compile statement. So as you saw that there, every single time we're going to be compiling player.cpp along with main.cpp every single time. And so the way that works, as I showed you before, is that you're just going to include it there. And for however many implementation files there are, you're just going to tack them on there at the end. So the next thing I'm going to talk about is a header guard. Now, the only reason I'm talking about these is because you see them there in the code. And I'm not sure if you've seen them before, but if I pull open that player code that I was looking at, you'll see that I've included these things here. Now, these are called header guards. And so let's kind of look at an example of that in the notes. And so what this means is when you see a pound if ndf, which means if not defined, some name here, let me do that. So this stands for if not defined, and then whatever that name is. So it's saying if this name is not defined anywhere, then define that same name and then in here is some code, and then on the bottom we're going to say end if. Now the end if just ends this if statement. You'll learn a bit more about that in CS 326, the end ifs. And so all I've done here is I have header guarded pretty much all of these files just to prevent some compiler problems. So for example, notice up here I've included in the player H file iostream and string. I've also included this thing random. And now if I come into main, you will see that if I pull player H up here, you have to kind of think about how this is going to work, in that it's going to include player.h very first thing it does. And so in player.h, the very first thing that this file does is include these libraries and defines these names, ios_h and rand_h. And so the moment that you can see that they've kind of dimmed themselves out there, right? So as soon as I include player.h, notice it's going to say if not defined ios_h, but guess what? It's already defined from player.h. So it actually does not include these libraries. And just like here, it will also not include these libraries. So the purpose of these header guards is to just kind of make our compiling life a lot easier. As you kind of get 1,000 files together for one kind of program implementation, sometimes you don't know where libraries are, and so you may wrap them in some header guards so that you can just include all of them and not have to worry about anything. So I hope you were able to follow that. This is pretty simple stuff. And so if I had to put that into words, I would say this helps us not include header files over and over again. The compiler does not like that. And then we're going to do one more thing. I'm going to talk about explicit conversions, and we're getting into the code now at this point. So an explicit conversion is when you convert a variable of one type to another type. Now this has to be legal, and it needs to make sense. So unfortunately, when you say string, let's say you've got somewhere int x equals 0, and then I say string x. Now this is how we explicitly convert. This does not make very much sense. It does not, and that's kind of why we bring in these toString functions that you've seen before. But when it comes to numbers, it's actually pretty easy to do that. For example, if we wanted our int x to be a float, we could very easily say, cout, cast whatever this is, convert whatever this is to a float, and there you have it. So we'll say that this here is legal, and this here is not legal. Now the reason I'm bringing this up is because I'm going to be doing it today when we talk about pointers. So I'll give you a little bit of syntax here for that. There you go. Whatever type 1 is, whatever type 2 is, and then you can make that expression there. All right, so now we're finally moving on to pointers. It's time for pointers. So we're going to start with addresses and pointer arithmetic. That's, I guess, the title of this. And the very first thing we need to learn about is operators. Now, I think we've already talked about some operators before, such as the dot operator and the scope resolution operator. When it comes to pointers, we're going to want to know a few operators. The very first one is the ampersand. Now, this was sure to be confusing because this is used in pass by reference. Though, the way that this operator is used is very similar to the pass by reference concept. So it should be easy to remember. So this happens to be the address of operator, which will return the address of a variable. Now this happens to be a unary operator. Now the term unary means that it takes one operand. So I kind of discussed that a little bit for you to know. Addition, in a sense, is a binary operator because you take 2 plus 3. Notice that 2 is one operand and 3 is the second operand. So that's 1, 2, that's bi. And so plus here happens to be a binary operator. Now this ampersand here is a unary operator, meaning it only takes one operand. So what that looks like is, say you have int x. Well, first we'll begin with this. Whatever the name of your variable is, you'll just apply the ampersand to that, and it should return the address of that variable. The address is a hexadecimal number. Just so you know. All right. So I give you some syntax here. And we'll actually go try it out right now. Right now in some code. So we're going to run that code, something similar at least. And let me make a nice little file here for us to get started. So today is the 15th, and we're doing pointers. And for that, we're going to want a CPP file. So we're going to start with ops.cpp. And we're going to drag this on into here. So let me grab my favorite stuff here. As always, we're going to do a nice include statement here. Maybe I'll make this a little bigger. I've kind of not been paying attention to that. And we'll just hop in main. We're not going to do any classes yet. No classes. We're going to take a little break from classes today. And I'm going to do exactly what I told you I'd do. So I'm going to declare some int x. We could assign it to be 0 if we want. And we're going to print whatever its address is to the screen. So just to prove to you that there's a few different things going on here. So if we see out x, this is going to be the variable of, this is going to be the actual value of x. Value stored, the value stored happens to be this. And then this is going to be the address. This is going to be the location. So notice here we'll print out a 0, likely, and then we're going to print out the address of 0. And then if I happen to overwrite x with, say, the number 947, and then I run this code again, likely we will see the exact same address, but a different value. So let's go take a look-see. And this file is going to be called ops, I believe. Looks like it went. So let's give it a run. Maybe I can zoom in here a little bit. And here you go. So notice that the value stored there was 0 to start. And then we've got this big hex number. I'll talk about hex kind of at the end if we've got time. But this is just a number. Okay. And then notice I overwrote 0 with 947, but we are still located at the exact same address. So that's the address of variable x. It can contain all sorts of values that we want, but it's always located at the same place in memory. So next, I'm going to introduce to you the dereferencing operator. Dereference operator. I guess I'm going to stick with my formats. I have to do a few... Oh, man. I really need to come up with some better... I need to come up with some better markers. How about this? That's going to be my little bullet point there. I don't want to use these stars because guess what? The dereference operator is a star. So I really don't want to use that. I also don't want to use that arrow because guess what? That happens to be an operator as well. So we'll get there at some point too. So this is dereferencing operator. And what does the dereference operator do? Well, it will, in a way, uncover the value stored at memory address. This happens to be a unary operator as well. And the way it will be used is we will dereference some address. Now I'm going to put this in little less than greater thans to indicate that this will be either a variable, it could be also a literal. So I'll give you a nice example of that. But first, we're going to do it this way. So say we have int x, and we wanted to do that classic thing up here where we see out its value, or its address, so we do. And then the next thing we do is we do it again, except this time I'm going to dereference that address. So I'm going to apply the dereferencing operator to this address here. Okay, so let's go into our code and just do exactly that. I'm going to dereference that address, whatever it is that x is stored at. Okay, so what we're going to see here is a little bit of redundancy. We're going to see 0, the address that it's stored at, and then we're going to see 0 again. Why is that? Because we're going to look at this address and dereference it, meaning we're going to uncover that value that's stored in that memory. So let's give it a shot, and then I'm going to show you something completely goofy. But only to prove to you that this operator works the way you think it would. So once we run it, notice that we've got the 947s here and the zeros here. So basically, we just reversed what we did with the ampersand. Now, if I really wanted to, I could do this. I'll even take out the... I could Get the address of this variable, dereference, get the address of it, dereference, get the address of it, dereference, get the address of it, dereference, etc. I do this as many times as I want. And I'll show you that it'll compile. Now recall this is a unary operator, so imagine that this is the very first operation, and then this is the very next operation, and then this is the very next operation. So notice it kind of happens one at a time. These are all unary operators. So let me go ahead and pull that in here, and guess what? We're going to expect to see the exact same output. You're going to say, this is ridiculous. Why does it compile? Well, because it does. So there you have it. There's our 0. So that's how the dereference operator works. Now, before we get started on the remaining operators, we need to introduce pointers. So let me pull up my notes here. And let me see what kind of time we're looking at. Looks like we're chugging along here pretty well. So I'm going to come down here. Let me grab one of my famous notepad headers. Hey. I'm going to put it here. And we're going to introduce the idea of a pointer. So we'll call that a address. An address is a hexadecimal number. In my notes here, I have it listed as exactly that. And hexadecimal means that it's base 16. So as you all should know, binary is base 2. The Dewey Decimal System is base 10. Hence the DEC in decimal, that's base 10. And then here the hexa specifically means 16. So these are base 16 numbers. How does that work? Well, it works just like the Dewey Decimal System, except you're going to have 16 total digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then in standard decimal, this is when you would append, right? This is when you start using 2 symbols to represent a number. But since we're in base 16, it then goes A, B, C, D, E, F. And that's 16 total digits. So, guess what? A happens to represent 10. B happens to represent 11. If you wanted to take, say, F0, well, let's see. Maybe not F0, but if we did, let's see. Well, we'll count up here, right? So we'll go 12, and then we'll go 13. E happens to be 14. F happens to be 15. And then we follow the same pattern where we're going to start over and add a 0 there. That is 16. 1, 1 is 17. 1, 2 is 18. So on and so forth. So it's just a different way to represent numbers. And all addresses are stored like this. So as you can see here, I see an E, I see a D, I see a C, I see an A, and sometimes you'll see B's too. Now we can see the address of variables. As I said before, we've got this wonderful operator to do that. Now, why do we ever want to look at addresses? Well, the answer for that is to control dynamic memory in C++. Now, how does this variable x get this address? Well, when the program is run, the program will request memory from the operating system. And the operating system will assign a memory location for this variable x. So before we write that down, let's mention the difference between a static and a dynamic variable. And so a static variable, and notice that this is not to be confused with static member variables. Recall that a member variable is different. That's where there's only one. There's only one for all of the objects in a class. I am talking about a static variable, which means that the memory is gifted before runtime. Memory is gifted before runtime. So what happens here is that this x, its address is static. Okay, this is considered to be a static variable because the address it has is given to it before runtime. The compiler kind of works that all out at the beginning, and it will assign that address to x before it even starts running anything. So if we start talking about dynamic variables now, the memory is, I'll say, granted, assigned during the runtime. So at some point during our program, we're going to say, hey, operating system, I need some more memory. And it's going to give it to us. So that's the difference between a static variable and a dynamic variable. Now, if we only use static variables, we never need to mess with the address. But it so happens we're going to be learning how to use dynamic memory. And so in order to do that, we need to understand dynamic variables, and we need to mess with the address. And I will show you how. That's where the pointer comes in. So let us start with pointers. What did I put here? Yep, we're already working on it. Pointers are variables that hold addresses. Pointers enforce the type of the variable. Now, I'll get to what that means in just a moment. But really, what it means is addresses have their own type. You say, that's ridiculous. An address is a hexadecimal number. How can it have its own type? Well, what's that address storing? Does it store a float? Does it store an int? We're going to talk about these things. So addresses have their own type. And so allow me to show you what a pointer looks like. We're going to want some syntax for that. And let me see if I can do it. There we go. This is some good syntax. So this is where things are going to get sufficiently confusing for you. So notice up here, we talked about using this as the dereferencing operator. Now, if we want to declare a pointer, we have to include this star in front of our variable names. So let us look at that in our code. So I'm going to make it int pointer. So I'm going to type int. Once again, we can just come here and look at our notes. And I could even just kind of copy this in here and replace it, right? So what am I working with? Well, I'm working with an int. And what do I want it to be? Well, let's call it maybe a pointer. So now this pointer holds this pointer can hold an address to an int. Now, right now, whatever this holds is nothing. Or we can't assume that, but we will want to initialize it to something. Now, we won't do null yet, but we can do this. And so now, if we happen to see out this pointer, we are going to see the address of X. Let's give it a shot. And what do you know? Here's the address of X. And notice that we stored it within a pointer. And we just printed that pointer. And we saw it, right? So here I am assigning to it. And then look, I didn't even have to call the address on it. The address of operator. This is an address. Pointers are addresses. Now, if I ever wanted to dereference this pointer, I could absolutely do that. By using the dereferencing operator. So once again, we run this code. We're going to get 947 out of there because we're just dereferencing that address. So now we're going to kind of bring it all back around to a few things. The first thing I'm going to introduce is another operator, and that's going to be the size of operator. Now this looks not like an operator that you've ever seen before. It actually looks like a function. But if you go on the if you go on the C++ website and take a look at this, it's actually considered to be an operator. And so what this does is it returns the size in bytes of a type or a variable. Okay, so let's just give it a shot. I would love to save that, so let me do that. Thank you, program. So if we happen to come into here and I want to see what the size of X is, I can print it. Now, X happens to be an integer. So how many bytes is that? Well, ints are 4 bytes, right? So if I type size of here and I put X in there, I could also put the just the type in there if I wanted to. So we actually have a few options here. So let me make sure that I include that in our notes, and that you can provide either the type or the variable. Oh yes, I already got it there. So let's go ahead and compile this, and I will show you that ints are indeed 4 bytes. What do you know? Size of X happens to be 4. What's the size of an int? It's also 4. So really, you can throw whatever you want into this size of operator, and it will tell you what's the size of that variable. Now I'm going to go ahead and move into kind of a new example here. And this one is going to be describing how dereferencing addresses work. As I said previously, pointers and addresses have a type. And it all boils down to the size of that variable. And so we're going to talk about sizes here. We'll guess the name of that. Size of CPP. Let's pull it in here. Let me go grab my favorite stuff. All right, so here we are, and if I took, say, the size of a double, let me actually declare a double first. This is going to be our double variable. Let's say it's equal to 3.14 pi. If I want to know the size of it, it'll happen to be it'll be 8. It'll be a total of 8 bytes. This will be 8 bytes. And so if I declare a double pointer, we can assign the address of that same dvar to the pointer. Now, as we dereference it, I'll just put in notes here. This dereferences 8 bytes in a double format. Dereference 8 bytes in double format. But what if I converted? What if I converted that address to something else? So let me show you. Do you remember up here when I talked about explicit conversions? Now, addresses can be easily converted to any type that you want them to be. And so let me show you the kind of wackiness that's going on here. And so we'll start with the deref double. And what does that look like? Well, as I said, we're just going to dereference the depointer. And we should see 3.14. But now we're going to get crazy. Let's deref this same variable as an int. And let's deref this same variable as a float. Well, how do I do that? Well, the very first thing I need to do is cast this address, or convert, rather. I need to use the right term. I need to convert it to a float type. Should work like that. I guess I wanted that one to be the int. And in this case, I want this one to be a float. So notice that this is a pointer for a double. I'm actually converting it to a pointer for an int, and then I'm going to dereference it. So this one dereferences, right? Deref 4 bytes in double format. This one derefs, not 4 bytes here, sorry. This one derefs 4 bytes in int format. And this derefs 4 bytes in float format. So let's go take a look and see what all of those come out to be. And what I'm going to prove to you is that numbers are represented in memory differently. So what I expect to see is that float value is going to be different than the int value. And perhaps the double value will be different than them as well. So I should have loaded this on here like that. And if we run this code, you'll see that when I dereference all 8 bytes of this double, notice that the size of it is 8. If I dereference all 8 bytes of this double, we get 3.14. But let's say I dereference only the first 4 bytes of that double into an int, and I get this number, whatever it is. And then let's say I dereference those only first 4 bytes in that double, and I cast it, or I represent it as a float, and I get this huge number. So what the heck is going on here? Well, this is best represented with maybe an Excel spreadsheet. Let me check in on my time here to make sure we're going well. I will probably call it a little bit earlier than I normally would class time. Since I can't take the time to answer your questions, I'm sure at this point I'm melting your brain. So if we have some memory here, likely if it's hex, we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, A, B, C, D, E, F, G. Not G, but 1, 0. And so a byte takes up, I believe, 4 of these. And so notice that these are going to be represented as bytes are kind of like this. They take up 8 whole spots, 8 bits. So it's like this: 1, 2, 3, 4, 5, 6, 7, 8. So that is 1 byte. That is 1 byte. And so in here, we're going to store some stuff. And so let's say that we take